Thank you and good morning. I will speak in French. I'm very glad to be able to take the floor today and try and convey to you interesting messages. I will talk about hybridization, selection, and valorization of selected strains, and then I will talk about the production of yeasts in the dried form with the easy-to-use process, which is something which is done in order to enhance the effect on the system. At the beginning, I will talk about hybridization and of the first screening of yeasts. Then I will give the floor to Jean-Christophe Crachereau, who will address us on the methods for selection and screening at the level of polyphenolic extraction. And then I will take the floor again, and we will try and stick to the time allotted to us in order to tell you about the specificities of easy to use. As you probably know, the needs of farmers, of wine growers, have increased in terms of yeast selection. And indeed, today we do not limit ourselves to make fermentations absolutely correct, but we also want to know what is the contribution coming from yeasts in terms of organoleptic properties and characteristics, which means that wine growers and winemakers indeed try and understand what contribution comes from yeast. And we talk here about aromatic features, organoleptic features. And based on them, we can, of course, benefit from all the features which are present in nature, plus we can also benefit from specific strains which have been selected so that the performance is improved in terms of analytical and organoleptic properties. And we have a number of techniques to do so, which include mutagenesis, whereby you have a mutation due to external factors of the yeasts, and then we have managed evolution, as is it called, whereby we put yeasts under stress so that they can react and improve as a consequence. And when we have, of course, genetic modification, and we also have hybridization. And indeed, I will address that as a powerful technique to improve the enological strains. Hybridization is a natural phenomenon. It is linked to our reproduction, and it happens only in specific features, in that you have the life cycle of Saccharomyces cerevisiae. And we know, especially at industrial level, that is the very foundation of everything, that the vegetative growth is what makes it possible to obtain biomass. And in no stress conditions, meaning in favorable conditions, the yeast or its spores, which comprise one part of the genetic information, can transform themselves, double in number, and create a biomass. What we are interested in especially, and what makes out the genetic material which cannot be changed, is something that happens in the central part of the process, and I'm talking about sporulation conditions, which means that yeasts are put in specific conditions and they can sporulate and they produce tetrads. And this entails meiosis, 4 spores sexuated, and you have this sexuation types that can be crossed, and it is the capability of these diploids that produce the spores that are at the very basis of hybridization. And these can come from different sources, from different species and strains of the very same species. So much so that at the end of the process, this will entail a number of changes and a genetic combination between the two parents with a possible adaptation of the offspring, so to say, strain. And then, of course, there are interspecific hybrids or intra-specific hybrids, depending on whether it is one species or several species. What is interesting here is the combination, the genetic combination of the two parent strains, which can also relate to metabolic aspects with a possible improvement of the strain obtained. With reference to the accomplishment of all this in the laboratory, of course, you start, first of all, selecting the parent strains. Let's consider this example with parent 1 and parent 2, which is the example that we will take into consideration in this presentation. Well, we had parent 1, one mother strain, which was interesting in terms of polyphenol extraction, fermentation, and also very good aromatic component and contribution vis-a-vis the requests formulated today in terms of sugar content and polyphenolic maturation. Well, that parent strain was no longer suitable in relation, again, to the sugar content and to the adaptation of conditions whereby there is a strong demand for nitrogen and slow fermentation. We decided, therefore, to hybridize this strain of this yeast with another yeast which had different properties, specifically with reference to the rapidity of fermentation and resistance to high sugar content and low nitrogen presence. And you see that with reference to polyphenol extraction and aromatic contribution, the properties were less marked than in the other parent. At the beginning of hybridization as a process, of course, you study the parent strains and you have to obtain sporulation. After doing so, you have to check whether spores can be used or not, and specific media are used. And there is also germination in a rich environment in terms of biomass in order to be able to retrieve a stable spore. Afterwards, the sexual type, either A or alpha, is analyzed via the PCR mating type approach, whereby you again identify the sexuated properties of the spores. With reference to parent 1 and 2 and to sporulation, the results were satisfactory in terms of ascospores obtained in this way. That was sufficient and satisfactory to continue the study. The germination rate was good. It was possible to obtain a good percentage of germinated spores, while we had an issue, and this happens sometimes, and it is a homothallism. What is it? It is the capability on the part of a number of strains to produce spores that can change their sexual type rapidly when you grow them in a rich environment. After the second mitosis, a spore of type A can become an alpha spore type, and this is a huge problem. And actually, the problem is that happened in our case. At a certain point, we could no longer distinguish A and alpha spores and hybridize it with a different spore. So this was detrimental for the traditional type of hybridization. The solution to the problem was identified in terms of micro manipulation, in that we let the yeast sporulate. We produce tetrads, which are then dissected so as to use micro manipulation again for hybridization purposes, and we bring together the spores of parent 1 and 2, and then we will see whether we actually performed this process properly and we obtained the diploid spores that we wanted. You see here the plate result. We dissect the tetrads directly after the formation of the tetrads themselves, and we put one spore of parent 1 on one spore of parent 2 in order to cross-breed them. And then we have basically three possibilities. Either you have a stable sex type A or alpha spores from parent 2, and then you can hybridize, but this form of hybridization is in strain 1, which will be a hybridization of the spore in parent 1, so it is not really a hybrid actually. And then a third situation, which is bringing together a spore of parent 1 with the inverse sex type of parent 2, which is a real hybrid, which means that the first thing to do is to do the PCR mating type in order to identify the type of diploid strain, and then eliminate the self-diploidism strain for parent 1 with parent 1, which meant that we did PCR-TY, and the transponents are in different loci of the genomes and in different points depending on the strains, so as to have a genetic profile that included two transponents and have a genetic profile of the strain itself. The starting principle being that you have higher possibilities if you have a diploid strain to have one part from parent 1 and one from parent 2, and they being real hybrids, which is not a self-produced hybridation. After obtaining that, you will have to select and make analogical screening. The first ones were sort of were considering the basic enological parameters. And in this case, we decided to go for fructose assimilation instead of glucose, which and less synthetic must in the concentrations that you see on the slide. These are the parameters that we selected. We did a series of real hybrids as a consequence, and we sought to understand what the final results were in terms of assimilation of fructose. You see there are huge differences. Parent 2 on the left-hand side is characterized by a fairly high consumption of fructose, and parent 1 on the right-hand side has a different situation in terms of assimilation of fructose, and that meant difficult fermentation conditions. With reference to that, we also selected an additional 8 hybrids which had the best features in terms of fructose assimilation. And then we did another screening with this more controlled synthetic must or IV type, and that made it possible to assess the kinetics and basic analytical parameters. Here you see the 8 hybrids in function of parent 1 and 2. You see parent 1 in conditions of 250 grams per liter of glucose fructose was slower than parent 1, and all hybrids that we selected vis-a-vis fructose assimilation or in relation to that were present with this rapid kinetics, which meant that we wanted to go for intermediate solutions whereby we had a fairly fast process, and yet also the best features of parent 1 had to be preserved. So this is what we privileged. That was our first analytical and kinetic screening, and based on that we selected 3 hybrids which, selected on synthetic must, performed in a very interesting way. If we want to extract better polyphenols, and if we have to have other benefits, of course we have to consider natural conditions and not synthetic ones. And I give the floor to my colleague. I will also address you in French. Unfortunately, I can't speak Italian. The 3 hybrid strains were selected in the laboratory, and the point now is to assess the usage under equal conditions while coming as close as possible to production conditions. To that end, we worked with red vinification of Merlot in an area which is definitely representative for Bordeaux wine in the Entre-deux-Mers area. The maceration conditions of the skins had to be the same ones for all units. We have an experimental winery actually at Entre-deux-Mers, and we worked there, we tasted, we homogenized the skins. We again retrieved the ratio between the lees and must in order to have the same conditions in the various tanks, and then they were taken to this experimental laboratory which is north of Bordeaux. We worked with the 200-liter tanks, whereby it is possible to have a mass situation and wine conditions which are very similar to what we would have in real life, which means that we no longer are at the level of microvinification, but indeed here we have conditions which are very close to real life. What you see there are the must features. This must is absolutely traditional, with a good maturity, with and ripeness, with a good polyphenol situation. The analysis of polyphenols for must given here are made on the following day. So we do the same and did the same in each for each tank, so that we could see immediately the fact that we had again retrieved and recreated the right skin to juice ratio. You have averages here, but we did this analysis tank by tank. Admissible nitrogen, assimilable nitrogen was also indicated, but it was not sufficient, so it will be replenished. With reference to the rest of the analysis, we use a control, which is a strain which is highly used in the Bordeaux area, absolutely safe in terms of fermentation. It produces little volatile acidity. It is considered to be neutral, and it is divised in the version F22, which is produced by Fermentis. And this is the reference strain for all tests that we do with yeasts, irrespective of the producer. I mean, we act as independent suppliers to several ones. And the 2 offspring strains were called 1 and 2. Inoculation 20 grams per hectoliter. Temperature was not that too high, 24 degrees. The chaptalization was also fairly interesting, and it had to be, in that we wanted to have resistance also at highest percentages, which is something that we also normally achieve now in the Bordeaux area. You see 15%. And then adjustment of the nitrogen was performed in order to come as close as possible to field conditions. I mean that one of the parent strains, which is parent 1, which is slower and which with a higher demand, was adjusted with more nitrogen when compared to the other strains, in order to compare and contrast it with the wine in the comfort zone where it would be produced. Then we did 15 days of maceration, and then it was taken out and pressed. And we also decided to keep only the free run mast in order not to have a bias that would be linked to the other type of mast. So we refer about and report about this type of analysis. The ratio between skins and juice that we had created in the beginning by weighing the various parts again was considered. We had to have similar situations. Then inoculation with selected bacteria, stabilization, filtering, and bottling. First of all, we checked whether the process was successful, and you see that actually implementation is positive, 80%, which means that it is very good conditions. In terms of fermentation kinetics, we have two extreme curves. PART1, as we saw in the lab, was 2, and the other one slower was 1. So we have something which is consistent with the laboratory analysis. So our control has a similar kinetics when compared to the hybrids. Malolactic fermentation. There isn't much to say here. We have malolactic fermentation with an inoculation that did very well. The different duration is linked especially in terms of malic acid to the initial period, because a number of strains consume more malic acid than others, but I could affirm and say anyway that we have no interference based at least on the studies performed. Analysis. We compared wine analysis in 2 moments. Before malolactic fermentation and after bottling. And we had a tartaric stabilization period of more than 15 days with a strong effect on stability, especially of polyphenols and anthocyanins, which are also influencing the color. In order to show to you the differences that we have in terms of alcohol content and volatile acidity, we see first of all that we have a difference, especially in terms of volatile acidity. The hybrid strains have a slightly higher volatile acidity when compared to the parents and similar to that of the control, but this is at a reasonable level. In order to further check what we were doing, we analyzed things during aging and after bottling, and the situation did not change. In terms of extraction of polyphenols, there are a few differences, and we see that hybrid A has a level of polyphenol extraction which is rather high. It is similar to that of the control strain, or even more than that, at the level of anthocyanins and tannins measured by means of the total polyphenol index. The two parents have differences in extraction, and the two strains A and C have an intermediate level. After stabilization, fining, aging, we have a decrease in anthocyanins, which is classic, let's say, but we still have the same hierarchy of polyphenol concentrations. And this is color. We have some differences emerging in this case between the end of the malolactic fermentation and the period after bottling. We see some shifts here, and the stability in terms of color differed for the different units. We have lower color intensity in parent, and after bottling, a more stable and intense color applied to the control and hybrid A and C.